Okay, so let me wait for two, three. Okay, so let's wait for 1 or 2 minutes more. Let's see how many else joins. Then we will start. Okay, so let's begin. So hello everyone, my name is Ruja Mukherjee and I'll be taking this live session for NPTEL course on reinforcement learning. Just like every other week, we will be solving some problems related to the assignment as well as do a recap of whatever was done this week, that is week number 6. So this session is being recorded. You can later watch it also on YouTube. Okay, so let's begin. So, I have thought about this class as a very good comparison of all the algorithms that you have known so far and what is the difference of what we are doing in every case. Okay, so let's start. Like, what was the objective of the MDP problem when we first was introduced to the MDP problem? Right. So we are given two functions, right? One was value function vpi and action state action function state action function qpi, right? These are the two functions were given, and our task us for any given policy pi, we had to find out, we had to basically find out this v pi and q pi for any policy pi, right? So what was the policy? Policy was basically a algorithm to solve your MDP, right? Your any algorithm you have to solve your MDP. Yeah, yeah, a map. Correct. It's a map. Mapping of state to action is your policy. Okay, fine. That basically helps you solve the problem, beat any problem. Okay. Now, uh, to solve MDP, what are the algorithms we have seen so far in our last 6 weeks? Last 6 weeks, what are the problems we have solved? We found dynamic programming. Then we came to what? Then we came to Monte Carlo methods. and last we came to this week temporal difference. Right. So like a brief way to understand, each one have their its own advantages, disadvantages, everything. But if you think about it, like one at a time and compare it side by side, you will find a clear way to understand what we are trying to do. Right. We were given a few Bellman equations. So we had Bellman equations to solve V pi and Q pi, right? And we also came across something called optimal Bellman equation, right? Right, we came across these terms. So, what we are trying to do using DP? We are trying to find out the best policy for our algorithm, for our problem at hand. Whatever game we are trying to play, whatever objective we have, we want to find out the best policy, right? So we came across this thing called GPI. So I'm just generalizing it, so that this picture of all the algorithms will be very clear to you. So I'm just trying to generalize all three of them together, right? So now you have been given a policy. You have been given an arbitrary policy. Pi. What are the methods we tried? We tried something called policy evaluation, right? What does policy evaluation does? Policy evaluation does that, given a policy to me, we need to check how good is that policy, right? That is our policy evaluation, right? You have that policy evaluation, then you have policy iteration, right? So what does policy iteration does? Policy iteration basically extract the best policy from the given policy you have, right? You have to find out the best policy from all the policies. Like it is used to improve your policy, right? Policy iteration or policy improvement, right? Let me write it improvement. So you have found out the policy, you have already evaluated the policy. Now you find out the better policy than the policy you already have. How do you do it? So you have your pi and you have your v, right? What are you doing? You are evaluating it. And then you are doing improvement, right? So this entire this thing, what is called? This is called GPI, generalized policy iteration, right? So this entire sequence which you continue throughout as long as you want to do, right? This is your generalized policy iteration, right? So all this, so if you have gone through the lectures, you have gone through the book, you know that this concept of GPI is applicable to each and all of the algorithm. Am I correct? So each and every application of the algorithm has this, right? So you have your policy evaluation, and then you have policy control or improvement, anything is called. So this cycle is the basic structure of every algorithms which you have seen, be it dynamic programming, be it Monte Carlo, be it your TD, right? So you are finding a pattern, right? So you have your algorithm, you can choose your preferred choice of algorithm, be it a DP, be it a your be it your like temporal difference, or be it your Monte Carlo. You have that. Now, what were we trying to do in DP? What we are trying to do in DP? So let's first revise what we did in DP. So in DP, we were given a policy pi. You are given a v pi, right? We prepared an update rule for v pi, right? We saw that how v pi, how we are replacing the value from the previous iteration, previous state to the new state, right? We saw that, right? So the tabular approach. So you have a tabular approach. So this one is your S and this one is your S dash, and you are like updating S dash states values, set of values from your previous values, right? That one was we are doing. So prepare an update rule for v pi. Then we did what we did. Then we check the max difference between some what was the max of delta comma v dash s comma vs, right? We are checking this, right? We are trying to do this, and if this difference was less than delta, if difference was less than delta, we stopped, right? Or else we used to continuously update it. You have to continuously evaluate it, right? So that was your what you are trying to do in DP, right? And why do you think it was called a dynamic programming? Because if you have attended a algorithmic course, what you have seen in an algorithmic course, that in a DP you have a tabular structure. You always like you remember if you have done the factorial sum using DP, right? So what you used to do is to store it and add it with the previous value and that. So here also you are trying to evaluate using a table. So this is why this algorithm is a DP algorithm, right? So this part is clear. This was one other evaluation. From evaluation, yeah, subset of problem. Basically, you are doing a not only subset of problem, but you are storing the subset of problem. Like subset of problem is also in your divide and conquer, but this is different. This is in DP. So DP, you are storing the solution of the previous layer and then doing it. Yeah. So so this one is your policy evaluation. So this part was your policy evaluation. So in policy iteration, what you do? What do you do? In policy iteration, you checked that suppose this one is your previous policy. So this one is your previous policy, right? And this one is your new policy, right? Let me do a better drawing. This drawing is not great. So this one is your previous policy. right? This one is your new policy, suppose, right? So how will PI update it? So okay, this one is a little confusing. So let me redraw it, like re-say it. Let me use it like this. So at so VQ, sorry, pi at S was choosing previously action. So sorry, so was choosing action Q1. Suppose suppose it was choosing action A1. Now the new policy, that is pi dash S, is choosing A2, right? So now you are now you will update the policy. Now you will update the policy because you know pi star is better than pi. You know pi star is better than pi because you have already done that, right? So what you used to do, you used to update it. You used to update the policy that okay, now from now onwards at state S I will choose A2. So that is your policy improvement, right? Now what used to do in this happen in this case? So in this case, one scenario is like this. So if you have something like this, uh, what I want to do, sorry. So suppose, so in this case, if I have to say that this is your evaluation and this one is your improvement. So if I start here from with V and pi, I will continuously oscillate like this to the end from, and it's a very big oscillation, right? So what can be done for to minimize it? So to minimize it, we came across this term called value evaluation. Right. So what was the difference in value evaluation? Sorry, value iteration. So it was kind of a squeeze in between policy improvement and policy evaluation. So what you are trying to do when you are calculating V pi S, while calculating V pi S, while calculating V pi S, update function V with only the action which gives best, which gives highest return, right? So while previously you are considering all the action pair problem like action pair bundles, now you don't. Now you are selecting only the one which is the highest pattern. So what advantages you give? You don't have to go through this rabbit hole of constant up and down zigzag. Now you can do take small stride and reach to the final destination of pi star. So you can reach pi star much slower, faster and easier, right? So that was your DP solution. Now, what is the interesting feature of the DP? What is the interesting feature of the DP? So in DP we assume for DP we assume that we have a pi is dash comma r given s comma a transition table available. We assume that this thing is available. Yeah, the term is bootstrapping, but in simple terms, why are you able to do a bootstrapping? Why are you able to do a bootstrapping? Because you have this prior information that, okay, these are the transition probabilities. So you are able to store everything up. So you are able to store everything because you know the entire transition probability table. You know everything from that where transition is possible and where transition is not possible. So you are exploring everything, and it is very costly. So that's the downside of your DP algorithm, right? That's the downside of your DP algorithm. Now let's come to how do you improve this. So we come across the next set of algorithm in the literature was Monte Carlo, and this is basically a sampling based algo, right? So this is basically a sampling based algo. So this assumes that you don't have the transition table. You don't know anything about the state transition table. No info about state transition table and update V is using sampling, right? Now again, let's come back to those terms: policy improvement, policy iteration. Like now, how are we going? How in Monte Carlo are you trying to get a policy policy evaluation? How are you doing the policy evaluation? So what you do is in Monte Carlo, the logic is that you sample, as the name suggests, you sample an episode. So now I guess everybody is comfortable with the term episode. What an episode does, right? So episode is basically a source action result part from start to the terminal state, right? So we generate an episode. Yeah, one computation until terminal state. Yeah, correct. So we generate an episode, sample episode, generate episode, everything is fine. Then what you do, you start from the terminal state and start adding them from our terminal state from that for that iteration, and you start adding it up, and value of each state. So start from end state and add up the value of each state is average of the returns for state S, right? The value of each state is the average of the all the returns at a state S, right? Okay. Now this is your evaluation. Now how are you going to update it? Now how are you going to evaluation? Now the part is your iteration or improvement. How are you going to improve it? So again, if we come back to this, what does this remind you? So this remind you of a greedy concept, right? So uh, this is kind of a greedy approach. Like when you are evaluating a policy, when you are generating a episode, so you are using the same policy to generate it, right? You are using the same policy to generate it. So this is basically a greedy approach. So every time you are averaging it out. So in a greedy approach, so in this case, what you want to do is you want to find out. So in a greedy approach, the problem is you always, what you do. In greedy approach, what do you do? Yeah, you always choose the best, right? So what you don't do is explore, right? What you don't do is explore. So we need to explore. At the end of the day, we need to explore, right? So in the exploding state, what do? You do what you have already done here, but sorry, let's get back to the earlier. To update policy, choose action that gives max QSA, right? So that's how you update the policy, right? So so for updating the policy, the concept is really different. That you can start at any state. So you don't have to always start at the start state. So like in this case, you always have to start from some start state S0. But here you can start from any state, S1, S2, S3, anything, right? So that is your Monte Carlo evaluation. Sorry, exploration. Next, what you got is Monte Carlo epsilon greedy policy. Right. So in previous case, you are not okay. You are not. You are still choosing the greedy one, right? You are not doing that exploration. Except what only this sort of exploration you are doing, that instead of always choosing this one, you can start at any place. You can start at any place. These are the only exploration you can get, right? Not much of an helpful, because in some grid solving problem, like say is an autonomous vehicle grid solving problem, it is not always that you start anywhere in the middle. You always start at the start and end at the bottom, right? So it is not necessary that this algorithm is very good practically. So what do? You do epsilon greedy policy. So what does this epsilon greedy policy say? It is quite similar to the previous one, right? There is only one difference, and this is a major difference. So these are your number of states. Right. So what does greedy epsilon greedy Monte Carlo does? What does this? What does this says about? What does the algorithm says? So the algorithm basically says that epsilon amount of time we explore and rest we choose maximum value. Right. So if epsilon times we explore and the rest time we choose arg max, then what will be the for each state? For each state, which action will you choose? Let me just rewrite it. Number of action, and this is a state, right? So here everything, there will be some q, the q attached to it. Right. So so how you are going to do it? So basically what does this mean? So in this entire statement, that alpha amount times we explore and the rest we choose arg max, this also it is implied to each policy will be considered at least by number of a. That means the total time you explore is epsilon. If there are a number of elements, so total number of times you can explore is at max epsilon by a, right? So that is your that is your concept for main concept for alpha greedy policy. So the rest, the non-optimal ones, can be chosen at the rate pi by sigma divided by epsilon divided by number of actions, right? So suppose this is your best policy So every value will be at least this. Right. So now what will be the chance of this? What will be the chance of this? That is what your greedy algorithm says. So the chance of this is 1 minus gamma plus gamma by number of a, right? So basically this term will indicate that it is epsilon greedy, right? So epsilon number of times it will dictate the argmax option. So 1 minus epsilon time it will not do that. It will always choose the best value option in that case, right? That is your first Monte Carlo, first visit Monte Carlo exploration using alpha soft policy. Now here comes the main part. Now comes the concept of policy versus on policy, right? So what is off policy and what is on policy? So the on policy means the random distribution of states is done via random sampling of episodes using policy pi. So using policy B, generate the actual module pi. So what does this mean? There is sharing which we are doing previously. So, so what does this mean? When the sharing of, while previously the random sampling of the episodes, the generating the episode, random sampling for generating the episode, and the non-random sampling for generating the the based module, the generate the module. Sorry, 1 minute. What I have written here? Generate the policy pi. Generate new policy pi for generate new policy using distribution pi. Right. So that is what difference we are doing. Previously we are using both pi for initializing, for random sampling we are also using pi, as well as when we are trying to when we are designing a new policy, we are updating the policy also using pi. So that is your online. So everything comes from the same source. What is in offline? In offline, what you are seeing before, both uses same distribution for pi like E. Right. So in off policy, both were using the same distribution. Evaluating some other policy while traversing some other policy. What do you mean? Evaluating some other policy while traversing some other policy. Yeah, correct. So that is so B is some other policy, and we are traversing some other policy for pi. So these are some nahi. So B is called behavioral policy, and pi is your target policy, right? Right. That is what this does. So this uses two different policy, right? But how can you how can two different policy, you are two different policy, but how are you able to do it? How are you able to do it? So this was done using some technique. So shall I do it here? I don't have page, but I can arrange it. Suppose you have E pi of x summation x pi of x, right? Basically this E pi is your estimate. Do I have to repeat the trajectory, or are you can able to do it? You know what is the improvement factor? Importance sampling factor. You remember that, or I do have to do it? Okay, I will still do it. 1 minute. Importance sampling. Let's just directly write it. I don't have that amount of time to do anything. But we do something called importance sampling. And there is a thing called importance sampling factor, which is called pi of xi, let's suppose, is basically multiplication of t is equal to 1, k equals to t, pi of aksk divided by b of b of ak sk. Right, so this is a sampling factor. Right, and using this policy, what we are trying to do, we are trying to find a policy which is independent of your sampling factor, with your initial sampling of the resources. So you can read the algorithm from the book. Okay, so now these are important sampling. Now what we have, something called temporal difference. Okay, so before moving out, let's revisit this again. Let's start with this statement. What is difference from dp? So what is the difference you note this from dp? What is the difference you find this from dp? So here you don't have to store, right? So it is much faster. Nothing you have to store. You have to just generate a sequence and do it. Yeah, true, not full. This is heuristic, completely heuristic. Just take the average. But then you have to traverse the episode, right? You have to just traverse the episode for each one. You have to just traverse the episode and do it. You don't have to solve every path and all. Yeah. Okay. So let's come to the last few models. Let me just open another Jamboard. This Jamboard is full. Now we come to temporal difference. So this case is quite similar to your DP as well as quite similar to your Monte Carlo. So why it is close to dp? So let me just, without waste of time, just write down the just let me write down the uh, main equation, simple equation for TD. Let me write it down. V of ST is equals to V of ST plus gamma V of ST plus 1 minus V of ST. V of ST V of ST plus alpha R of t plus 1 minus alpha V of ST plus 1 minus V of ST. Right, this is your temporal difference algorithm. So first scene, what you see is that you are updating based on this. You are updating V of ST from V of we are updating V of ST from V of ST plus 1. Right, that's it your from your TD0. Right, else you can find out the if you have knowledge of the background knowledge, you can just find out the argmax, because it is not much difficult. So right, this was your TD0. So then next what you have? Next you have TD0. So this one is your evaluation. Now also you can use the same equation for your state action value also. And this algorithm is called SARSA, state return reward, state action return reward, etc., etc. State action reward, action, state action. Right. So this is what your does. So what you do is here is basically replace the VT with SA, T and everything, nothing more. So one quite difference is that there is only one quite difference. So so here VST depends on V of ST plus 1, right? But here, so what you have to do it, so from your corner when you are sitting here, You only need to observe the previous state. But in SARSA, what you need to do, you need to check the state as well as the action. You are basically filling out the this part. So this is your, let's say, ith 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 value function, ith state, and this is your, let's say, so this is your ith state, right. This is your ith state, and then you go to jth state using j plus 1 state. You go from state sij to s of j plus 1, right? Another, you have to take the another action for this. For this you have to take another action here, nothing more. So previously only you have to select the best one, like only select the value function, but here you have to select both the value function and both the q function and the next action, right? Next state and next action, nothing more, right? So now these were in on policy, these are all on policy, right? And the simple trick for doing not the on policy but your off policy was to replace this part. You replace this part. You replace this part and choose the action that is giving you maximum reward. Instead of this, you choose this. Instead of this, you choose gamma max gamma max of a q a star a. Right? Simple, nothing difficulty to understand, because, and here you have to just look ahead one state. So previously what you were doing in DB, you are just looking ahead up to the terminal state. Here you don't have to do it. You have to just look at the previous state, nothing more. That's the fundamental. So, and this is your off policy. I'm not going into details like expected SARSA and everything, because you can read it or you can follow the lecture. But this was the complete highlight of all the three algorithms, right? And this one is just sits in the middle of TD0 just sits in the middle of Monte Carlo and DB. Okay, nothing more. Okay, so you have any doubt regarding all the three algorithms, you can ask. All the three states of problems, you can ask. Okay. So give me such use cases on off policy and policy. Okay, okay, okay. Come. Visible. Cool. Okay, so this is, I guess I have set it to off policy. Let me just check it again. Okay. One thing I forgot to mention. One thing I forgot to mention. Uh, One thing I just forgot to mention. So this one is your Q learning. This max function is your Q learning. The best algorithm you will find. Let me check. I have written this one. Okay, so let's run. So last week we went through that frozen lake problem, right? So you have those, you have a lake. So you have this problem. You have this grid. Right. So here was your starting position, and here was your end position, and there was some ice, right? Some ice or some lake, right? So that was your. So you have to skip up those things, and you have to go, right? Let me just run it. One more thing I need to check. I guess I have given some problem today. On policy and off policy. No, no. Yeah, I haven't given anything. Okay, so we have still running. One thing I will say that if you have gone through the book, in the book there are good examples of how on policy differs from your off policy and how it is better and all. Uh, you can go through those book examples. Like I remember that they have that yeah, like wind flying on the wind or some example of their cliff walking problem, right? So that was there. So that thing you can do. Mm, so so if I remember it correctly, it was something like this, the cliff hanging problem. So so you had this. So you have this cliff. So there was some. So there is always a negative reward of minus 1, but negative reward of minus 100 if falls from the cliff, right? So what you saw in that example was that, suppose if I start from here, so let us consider two. One was Q learning, where we always choose argmax, right? So in that case, it will just go like this. It will take the shortest algorithm, what was found from the simulation. And in your normal Monte Carlo, what will happen? It will go here and then come here. So it will always play safe, right? Okay, sorry, I haven't shared it, right? Sorry. Yeah. So this was the problem, right? So you have this you have this cliff walk the cliff problem, walking on the cliff walking problem. So you have this cliff. So you are given minus 1 reward for every step you take. You get a minus 1 reward and minus 100 in case you fall, right? What you saw in case of Q learning will always choose the shortest path. Will always choose the shortest path. And if you are using normal Monte Carlo, normal not Monte Carlo, uh, you are using TD. If you are using TD, it is always choose the safest path. It doesn't bother to it always, okay, you will reach the goal. It is not a problem, you will reach the goal, but the problem is that it will not choose the shortest path. You will just it will just try to play safe, that I will not take the risk of only of falling down. So is this use case like, is this use case enough, or you need to understand more? So Q learning is a best case of is basically online, off, not off policy. This is on policy. Q learning is off policy. Sorry, my mistake. So why it is called on policy and off policy? Why the term on policy and off policy? These names are very significant. So it is called on policy, the normal TD algorithms and all, because you see you are updating the policy on the go, right? You're not saying that, okay, I am using only one policy to both explore and both update. So I'm doing that using one policy, right? But in off policy you are using two different one. So one you are using for exploring, right? You are doing your exploring using one policy, and another policy you are just using to get your best policy out. So that's why one is called behavioral policy, another is called target policy. Alright, I will ask you to just go through the book and read the examples. The examples are very clean. I remember that first few times the blackjack problem that was given in the book was very difficult for me to understand, but after a few times I got it. Like it was a very good example to follow. Also, the book is very easy to read compared to the lectures, I would say. Okay, so let's move on. Let's solve the problems. Okay. So first question is Monte Carlo search tree. So in the search procedure listed in the lecture for Monte Carlo search tree, what is or are the uses of depth parameter? Have you got the paper for Monte Carlo search tree? Did you get the paper for Monte Carlo search tree? I will give you the very good place to read it. Let me open it. It is, so you should read it from here. These are much better source to read. I will say than the. Okay. So what will be the answer? So why you are using the depth parameter? So the depth parameter is used for few reasons. So the depth parameter gives you the chance to find out the leaf states. Uh, so depth parameter gives you the chance to find out the leaf states, right? It also allows you to find out the terminal states. Does it allow you to find out the terminal state? No, terminal state is found how? Only if the reward is 0 in that case. And so this one is correct. I was to identify the terminal leaf state, because in that case depth will be 0. Depth will be max depth, right? And the leaf state can be used to impact the choice of action, because once you leave the leaf state, you choose an action, allows us to specify the value function based on the number of steps has been taken. Sure. So I will suggest you to read this article or medium for Monte Carlo search tree. Okay, let's go to the next one. Suppose you are given a finite set of transition data. Suppose you have been given a finite set of transition data. Assuming the Markov model can be formed with the given data, is the actual MDP from which the data is generated, will value function calculated by MC and TD necessarily agree? So you have been given a transition data. now you are using MC and TD. Will the V pi calculated from MC and TD will be same? Give me some answers. Why will it be same or not? Yeah, why no? No is correct, but why no? Why no? So, yeah, so typically the answer is like that you don't need transition dynamics for your transition dynamics is not of any use for your Monte Carlo. For your Monte Carlo, you are simply doing your you are simply doing your sampling, right? You are simply doing a sampling and nothing more. So transition dynamic is not required for MC, but for TD, is it required transition dynamic? Answer it. Is TD transition dynamic is required? So TD transition dynamic is required, but only you need to know the next state transition, but not for the whole. You don't need the whole package. You just need the small portion. Just need the VS dash. For VS, you need the next state, nothing more, right? So yes, it is required, and that's the reason both will give you different results. Both will give you different results, and so that's why it will be it will not never agree. Okay. Sampling for TD, what you will have? You will have transition data only for next state, right? Okay, so let's come to question number 3. So in the iterative policy evaluation process, we have seen use of different update equations in DP, MC and TD. With regard to these equations, TB and TD make use of estimates but not MC. TD makes use of estimate but not TP, not MC. TD makes use of estimates but not DP and MC. MC and TD make use of estimates and not DP. All three makes use of estimates. So what will be the answer here? So answer will be all three of them requires estimates. So recall for DP what you are trying to do. So you are trying to calculate V pi using that pi PA probability R comma S dash given S comma A R plus gamma V V pi plus 1 V pi S. Right. Now what is this part? What is this part? This part is an estimate. Right. This calculation comes from your estimate. Right. This thing is estimate. Right. This thing is estimate. What is B pi? Right. This is what V pi is. Right. So you need an estimate in dp. Let's come back to Monte Carlo. So Monte Carlo, what you are doing, you are traversing from the back and you are adding up and summing it up, right? You are doing an average. But the equation what you are using? So the equation you are using is G is equal to gamma G plus RT plus 1, right? So again you are estimating. So you are basically estimating. Again you are estimating the G values. And last TD. TD also same. TD also you need VA plus S plus 1, right? So all three of them are using estimates. No one is. So basically you are averaging it out, right? Here you are in Monte Carlo you are averaging it out. So averaging is also a DP, is an estimate, right? Estimate of the estimate formula basically boils down to an average. If you remember the estimate value, so if somebody gives you an find estimate of x, what you are trying to do is basically summation of xi pxi, right? Which is basically, if you take an average, is 1 by n summation of xi, right? That is what your estimate is. So averaging it also is estimation. Okay, so the correct answer is all of them are makes use of estimates. Okay, so let's go to the next one. So is it necessary for behavior of an off-policy learning method to have non-zero probability for selecting all actions? Is it necessary for behavior of non-policy? So I didn't touch on it in much. Didn't touch on it much, but let me just derive it now, since I have got lot of space here. So suppose you sample x according to b, right? So you have b, so you are sampling x according to b. So you are asked to find estimate of pi with respect to estimate of x with respect to pi, right? Pi is target and b is behavioral uh, behavioral policy, and this is your target policy, right? So you are being asked to find this value e of pi given xn. Fine. So let's derive it. Okay, this will be a very good task. X belongs to x, x of pi of x. Right. Now we can write it also as like this. X belongs to x, x of pi x, b of x by b of x, because these both cancel out, so we can write it like this, right? Now we can again write it as like this. Summation x belongs to x, x into pi of x by bx into p of x, right? Now what is this? Summation of x bx. What is this? This is basically estimation of x with respect to b, right? This is basically estimation of x with respect to b, right? So now we will do some tactics. So we will write this as x belongs to x, x into, this is called importance factor, and we denote it as rho x, x of rho x into bx, right? Now using this thing, so bx, and this is another part, right? This is another part and this is another part. So this is one part and this is one part, and you compare it with this formula, so it will become expectation of, so this is basically expectation of x rho of x given b, right? So this is the expectation we are trying to calculate, and then you can do the rest of average sampling. Now the question here is, so this is your behavioral policy and this is your learning policy, that is target policy. Now the question here says it, if this is 0, is it possible to select this is 0? The obvious thing you will say that no, that is not possible, because then this will become 0 divided by this divided by 0, which is not a number, right? So that is not possible. That is the answer I will expect, right? But there are techniques which people have come out and to remove this. So one way you can do is weighted one. You do a weighted sum instead of this. So if you go at the book, so they used to do a weighted one. So instead of directly putting bx there, you do a weighted bx. So this was basically a multiplication chain. So you do a weighted multiplication chain, and then if only one state it is s, that is not going to be a problem, right? That is not going to be a problem. Any other state will be there, right? So that means you have not selected one state, but you are selecting other state, right? So that's why it is not going to be a problem. So it is not necessary. So answer will be no. It is not necessary that the probability will be 0, non-zero. Answer will be no. Okay. So now we come to this part, expected sarsa and sarsa. So with respect to expected sarsa, is exploration required as it is normal, as it is in normal sarsa and Q learning? Expected sarsa. So expected sarsa is, what is expected sarsa? So expected sarsa is basically this. If you remember this, which I wrote. So in expected sarsa, so this is your okay. Should I write the let me write the sarsa first. So sarsa, what is the update rule in sarsa? Sarsa, the update rule is q of s comma a, basically q of s comma a plus alpha r plus gamma q dash s dash minus q of s comma a. Right. So this one is your q function. So this is called sarsa. Why it is called sarsa? Because you need a state, you have a state, against your action you get a reward. This is your reward, this is your next state and action, right? So okay, fine. uh, Sorry, q of s dash comma a dash, right? Okay, fine, cool. Now uh, now in expected sarsa, what happens, instead of directly putting this q value of the next state, what you can do, you can put an expectation value, expectation of q. Instead of putting a directly the q function, what you put is an expectation of q, and that is called expected sarsa. Right, and then you have your q learning. What you do in q learning, you just simply take the max instead of this expectation or q dash thing. You just take the main, take the max q for state is dash, you select the max q, right? So it is said q learning is a special case of expected sarsa. Okay, now here it is said, is exploration required as it is in normal sarsa and q learning? Exploration is required in whole of td, right? So exploration is required in expected sarsa also, else it will not be able to function. Okay, so let's go to the next one. Assume we have available a simulation model for a particular problem. To learn an optimal policy, instead of following the trajectories end to end in such an iteration, we randomly supply a state. uh, so assume we have an available a simulation model for a particular problem. To learn an optimal policy, instead of following trajectories end to end in each iteration, we randomly supply a state and an action to the model and receive the corresponding reward. This information is used for updating the value function. Which method of the following is expected to work in this scenario? So what does the simulation is giving us? It is only giving us the reward. You give a state and an action, and it is giving us a reward. Does an MDP does that? What is the function of an MDP? You have a state and action, you give a reward, and you also get a new state. Right? So expected sarsa, Q learning are all required the next state, irrespective of it, because you need to calculate the Q S dash A dash, or max Q S, or estimation, right? So in all of the three, you require the next state information. Otherwise, you cannot proceed. Okay. So that is the answer will be none of the above, because obviously you need the next state information. Only reward will not be able to help you. Okay, so let's go to the next one. Okay, let's try to solve this. So these are two episodes. Right, you have two episodes. Estimate the value function using the first visit Monte Carlo evaluation. Okay, so let's start. So you have been given this episode. Okay. So this is episode number 1 and episode number 2. Right. Let's consider first episode number 1. You have been given first visit. So from where we start the episode? From this side or this side? So you start from this side, right? You always start from this side, from the last date. Okay. So what will be? So G initial will be 0, and now we will update it. So just for the sake of thing, just let gamma equals to 1. Okay? So G equals to 0 plus minus 3, right? So it will be minus 3. Now the first visit, if you remember what first visit and always visit is, in first visit you update it when you reach the last time you visited, when you last time visit the state. So in this case, Q is not the last time we are visiting, we will again visit later. So that time we will store it. Okay. Let's write P and Q here. VP and VQ. Let's, for the sake, write it here. VP and VQ. Okay, now we are not updating because the last, only the first time we visited, then only we will. Like means the last time we visited in this side. Okay, first time this side, last time that side. Okay, so last time. Okay, so now let's come to here. Here, G becomes 4 minus 3. You are carrying forward this, that becomes 1. Right? G becomes 1. Now this is not the last time that we are visiting P. Fine, so we are not adding it. Now G becomes here. G comes here. Is the first time last time we are visiting? Yes, so we have to update. Okay, so it is now current is 1 and now we are adding a reward of minus 4, so that will be minus 3, right? So the last time we are visiting, so we'll add it here. We are adding it here in a list of all the returns for G state BG. So okay, fine. Next, next what? Next we again go. Now we come here. Current reward is minus 3, and we are adding plus 2. That is minus 1. This is not the last time we are visiting P, right? So we will not update it. And now we come here. So G equals to minus 1 plus 3 is equal to 2, right? So this is the last time we are visiting P, so we'll update VP 2. Okay. Now let's come to these equations, the episode 2. Now let's come to episode 2. So let's come here. This is the last time we are visiting. So again G equals to 0 initially. Now G equals to, for this state, 0 minus 3 minus 3. This is not the last time we are visiting Q, right? We are again visiting Q, then minus 2 part. Then we come here. Now G is equals to minus 3 plus 3 equals to 0. And this is the last time we are visiting P, so we are updating it. So we are updating here. And then we come to last one, Q. This is the last time we are visiting Q. Yes. Minus 2, and we are update minus 2 here. Okay. So now let's do the average, because we have to do the average exactly here. So V of P is equals to 2 plus 0 divided by 2 is equals to 1. V of Q is equals to minus 3 minus 2 divided by 2 is equals to minus 5 by 2, right? Yeah. So the correct answer is 1 comma minus 2. So correct answer is option C. So any doubt regarding this, right? So any doubt regarding this calculation? These are easy calculations. Yeah, so if you haven't followed it, you just go and watch this back on YouTube, and you can do it yourself only. Again. Okay, so let's go to the next one. So the next one we will be using the same data. You will be using this same data only. So let's do it. So what they are saying is, now we are doing every visit. Instead of first visit, we are doing every visit. So we will update. We will update value func at each visit. Okay, fine, let's do it. So like always, we will write the VP here and VQ here. Okay, so let's start. Let's start one by one. So okay, so we need to carry forward that episode. Okay, so this is the episodes, so let's start it. Let me use some different color. Okay, so let's give the g value, start with the g value. So initially the g value will be 0, fine. Then we do g is equals to, start from here again, 0 minus 3, and we update the value of q, that is minus 3, what we observed here. Then we have 0 equals to g equals to minus 3. Now we come here, plus 4 is equals to 1. We update the value of 1 vq, that is 1. So this done, now come here. G is equals to 1 minus 4 equals to minus 3. Minus 3. Q value will be given minus 3 again. Then we come, this one done, then come here. G is equals to minus 3 plus 2 minus 1. Now we put here minus 1 for VP. Now we come to the last one. So this one done, this 3 minus 1 is equals to 2. So we update 2 here. Okay. Now we have to do the same for this one. So initially g is equals to 0. G becomes 0 minus 2 is equals to minus 2. This one done. So minus 2 will be here. Then g is equals to minus 2 plus 3 is equals to 1. That will be here. Then we come to this, g equals to plus 3, this one on this, g equals to plus 3 minus 2 is equals to, sorry, I made a mistake here. One minus 2 is equals to minus 1. So this will be minus 1. Did I copy something mistake? Oh, sorry, I made a mistake. Minus 3, it will be minus 3. So if it is minus 3, so this will be minus 3. Let me just erase this. Minus 3, so you will add minus 3 here. Then g is equals to minus 3 plus 3 equals to 0. So 0 will be added here. Then g is equal to 0 minus 2 is equals to minus 2. Minus 2 will be added here. So this total sum is basically minus 11, and we are dividing it by 4. So that is your value q. Now for value p, we are getting So you are getting this value is total 2 divided by 4, that is 1 by 2. So the correct answer is option C, minus 1 by 2 VQ minus 11 by 4. Yeah, correct. Okay, so let's go to the next one. Consider a Markov model that explains the observation given in question 7. I mean, same question. In this model, what is the probability transition from P to P itself? What is the expected transition of reward on transforming from Q to P? Okay, so let's draw the model first. Let's again write it down. It's difficult to write it down every time. I should have copied it every time. Plus 3 plus 2 minus 4 plus 4 minus 3. P plus 3, P plus 2, Q minus 4, P plus 4, Q minus 3, that is one episode, 2 episode, other episode is plus 3 plus 2 minus 4 plus 4 minus 3 minus 2 plus 3 minus 3 minus 2 P plus 3 Q minus 3. Q minus 3. Okay, so these are the two episode tasks. Now we have to draw a state transition diagram. Okay, fine, cool. So you will have, let me change the color. So you will have a state P, a state Q, and a terminal state. Okay. So if you look, P goes from P to P. P is making a transition from P to P. P is making a transition from P to Q. P is making a transition from P to Q. Okay. Similarly, P is making a transition from P to Q. So these are the two transitions that is possible from this state, P to P and P to Q. Right. So 4 times there are transition from P to something. Only one time P to P, only one in this case, and P to Q 3 times this case. Right. So now look at this time. So it will be 1 by 4 times it will make this transition, and 3 by 4 times it will make this transition. Simple probability. Okay. So from P it will make only these two transitions this amount of time. Okay. Now from where Q does, Q ends it 2 times. So Q to T, this is T, is 2 times. Other times it is Q to P. Q to P 2 times. Here is one Q to P, another is here Q to P. So this transition probability is half, and this transition probability is half. Okay. Okay. So now we need to find out the value functions for each of these steps, right? So P to P, how much value we are getting? Only one term, that is we are getting 3. 3 as the value. P to Q, how much we are getting? 2 plus 2. P to Q here is plus 4, and here P to Q is plus 3. So that is 9. 9 divided by 3 is 3. So it will be also 3. On an average, you are getting 3 plus 2 plus 2. Just you need to simple add it and do an average of the total reward. Okay. Now from Q to P, how much we are getting? 2 times. Minus 4. Minus 4 we are getting Q to P. Minus 4. Another one we are getting minus 2. So that is minus 6 divided by 2 is equal to minus 3. Minus 3. Now Q to transformation, minus 3 minus 3. So again minus 3 plus minus 3 is equals to minus 6 and divide by 2 minus 3. Correct. So this is your state transition diagram. This is your state transition diagram. Okay, any doubt regarding this?
Sir, how did you get that probability ratios? That P to P is 1 by 4th of probability like that. P
Yeah.
to Q is 3 by 4. How did you get that, sir?
Yeah, so you look at that P to P we are making only one transition. From P you can go either. So if you look at this, let me again do it. Let me again show it. So if you look at this one, so from P to P we are making only one transition here, right? So from P we can and another one is P to Q, another one here is P to Q, another one here is P to Q. So there are 4 transitions happening from P.
Okay.
So
Okay.
only one time we are going from P to P and 3 times we are going from P to Q. So it is standard average. So 1 by 4 and 3 by 4.
Okay. Thank you, sir. Thank you.
Okay, so this one is done. Let's go to the next one. So what will be the value estimate if batch TD are applied to the above transaction? What will be the value estimate? So simple way to do this is you have your value P and your value Q. You just directly apply your Bellman equations. Right. So from P to P, you have one action. From value P, you can your next state is either. So think about the next state. So since you are only worried about your TD0, so you only think about the next state. Some P you can go to P to P is you can go to next state, or you can go to P to Q, right? So let's apply the same. So what is the probability of going from P to P? That is 1 by 4. What is the reward? Let's go and check the reward. P to P, the reward is here. Reward is 3. Check this one. Reward is 3. So it will be 3 plus V of P, Bellman equations, next state, plus 3 by 4, right? How much value we are getting from going from P to Q? 3. So we'll write down the 3 here, plus again value of Q, just the Bellman equations. Then you have for VQ have 2 transitions, from this to this or from this to this, right? So let's write down that half. So let's down to, let's first write down the q to p equation. So what is the value you are getting? Minus 3 plus v of p, the next step, plus half minus 3 plus v of t. Now what is v of t? So at terminal, value is 0. So this part will be 0, right? So if you simplify these equations, this one will come out to be v of p is equals to, if we add this one up, 3 plus 1 by 4 v of p plus 3 by 4 v of q, right? And this one will come out to be minus 3 plus v of p by 2. Now you just need to solve this equation, equation 1 and equation 2, you will get it. So that if I solve this equation, let me see if I can do it short. Okay, I am jumping some steps here. So this will become, this equation will boil down to 3 by 4, 3 by 4, 3 by 3 by 4, 3 by 4 Vp, three by 4 v of p is equals to 3 plus 3 by 4 vq, which will become, if we cancel it out, vp is equals to 4 plus vq. Now you substitute it here. If you substitute it here, it will become vq minus 3 plus 2 plus v of q by 2, or v of q will become, this will be plus 1, this will go that side, so it will be minus 2, minus 1, minus 2. So v2 will be minus 2, v2 will be minus 2, and vp will be 4 minus 2 is equals to 2. This will be the answer, 2 minus 2. Okay, so so at the end of the day you have to solve the equations, nothing more, right? So any doubt regarding this? So okay, this one was the last question which I had. So any doubt you can ask. We will again meet next week. Yeah, thank you for joining. Okay, we will meet again next week. So if you have any doubt by then, you can again join next week. Yeah, bye.